Welcome back to Data Every Day. Today on Data Every Day, we are having a strange dataset, a gender classification dataset, where we'll be trying to classify gender based on personal preferences. The reason I say it's strange is if we look at it, first of all, there's only 66 rows, 66 examples. In addition, there are only these 4 very specific features, and they don't seem like they're going to have very much impact on the gender classification. My guess is, first of all, we're not going to be able to get accurate results because there's so little data, and second, I don't think these columns are going to be giving us good predictions for the classifications themselves. So this will be more of a video to show you what the limitations of using a low-quality dataset would be. So let's go ahead and import our libraries. We're starting with NumPy, Pandas, Matplotlib, Seaborn for visualization. Then we're just using the train test split function from sklearn and TensorFlow for training our neural network. So that's imported. Let's just load in our data using the pandas.readCSV function. And we can get the file path right over here, paste it in, take a look at the data. Here it is like we saw before. Again, only 66 rows. I don't know how we're going to be able to train on this, but we'll give it our best shot. So first of all, we notice that everything is in text format. What we should do is we can call this function a pandas function .info, which will give us some general information about each column. And you can see for each column there's 66 non-null values, and since there's only 66 rows, we know that this dataset actually has no nulls. So if we check the nulls in each, you can see 0 for every column. And additionally, as we said before, each column is a text or string data type. So let's see, how are we going to do this? Let's start it up here. Pre-processing. And I think the only thing we really have to worry about is encoding it. And we'll use one-hot encoding for every one of these. In fact, actually, why don't we use ordinal encoding for favorite color, right? Because you could say that let's see, data sub favorite color dot unique. Right, there's only 3, and they sort of go in ascending order. You could say cool is less than neutral, which is less than warm. So and it's already in the order that we want. So we can use this list as our actual ordering. So I'll go ahead real quick and just say color ordering. Let's go to that. And now let's just one-hot encode everything else. This is one-hot encoded, this is one-hot encoded, this is one-hot encoded. So there's no ordering between them. And for this we'll use a binary encoding or a label encoder from sklearn, which actually I should import here. sklearn.preprocessing import label encoder. Okay. So what we should do is let's take a look at the unique values for each. So if I let's see, I can get a dictionary which will give us a column matched to that column's unique values for every column in data.columns. This should give us, let's make it a list actually. Oh, no, let's make this a list. And we can see, alright, the thing we're looking for is if there's a duplicate value in between any 2 columns, and it looks like there is. other is shared between these two, right? So the problem with one-hot encoding here is if we encode this with one-hot encoding and encode this with one-hot encoding, we'll have two columns, both called other. So in this case, what I like to do is make a quick function called add prefixes, and that'll take in some data, a column to add prefixes to, and a prefix. And this will simply be, we'll return, let me call this df to avoid confusion. We'll return the data frame indexed at that column, but with the lambda function applied, that will take in some x and return prefix plus x. And we know x here will always be a string, so this was fine. For example, if I just show you what that looks like, if we wanted to add the prefix to our, which would it be? Favorite soft drink. And the prefix we want to add is s underscore. That will give us s underscore will be put onto every single value in here. And that will mean that we'll have s other. And we can distinguish that from, we could call this b other, right? So we won't have duplicate columns when we do the one-hot encoding. And so let me just go ahead and add the it looks like the only ones we have to add are these two. So let's just do that. Data sub favorite soft drink is equal to that. And we'll do the same thing, but for this is favorite beverage. And here we'll use B. So if we run that, and then we take a look at the data again, this has all B's, this has all S's. Now when we one-hot encode, we won't have any duplicate columns. So we can create a function now, one-hot encode, that will take in a data frame, a list of columns, and for each column, in columns, we will get the dummies matrix, which we'll just use pd.getDummies of that particular column. And if you're not sure what this does, you should just try it on favorite color. You see it takes all the unique values found in here, constructs new features from them, and for example, example 0 had cool, so there's a 1 for cool, a 0 for everything else. Example 1 had neutral, so there's a 1 for neutral, a 0 for everything else. And example 2 had warm, so there's a 1 for warm and a 0 for everyone else. That's why it's called one hot. There's 1 for each row. And so we'll get that dummies matrix for the specific column. Then we will concatenate pd.concat the data frame, the original data frame, and the new dummies matrix or data frame along the column axis. And then we will drop the original column from which the dummies were created. So this will take our data frame, find the column that we want, construct a dummies matrix from that column, concatenate it onto the end, and then drop the original column. And then we'll just return that data frame when we're done. Okay, so now if we try this, one-hot encode our data, and the columns here are just going to be all 4 of these, right? Actually, not favorite color, right? We're not one-hot encoding favorite color. Okay. That we'll keep favorite color, we'll keep gender. All the other 3 have been dropped, and they've been replaced with dummies matrices, or dummies data frames, concatenated onto the original data frame. And so that looks good. We'll just set that equal. And now let's process the favorite color. So we can do a very simple way of doing this. We can apply a lambda function to this data, to this column, right? And we have up here the color ordering. Let me just move it down. And basically, we can apply this x. So for every x in favorite color, for every one of these values, we're going to change it to be color ordering dot index x. And since color ordering, if we just look at that, looks like this, right? The index of this is 0, the index of this is 1, the index of this is 2. So if we take some value, let's say neutral, and we plug it into the color ordering dot index, it's going to get the index of that value. And the index of neutral is 1. So x, which was originally neutral, will become 1. And for each one, we're basically going to encode each value to be the index of that value in our ordering. So if we look at that, you can see now it goes from being cool, neutral, warm, warm, cool to 0, 1, 2, 2, 0. And let's just set data sub favorite color equal to that. Okay. And now, right, let's just take a look at the data here. You can see the only thing left to deal with is the gender, and we can do that using sklearn's label encoder, which we imported before. So encoder, I'll call it label encoder, is equal to label encoder, and the gender column is going to be label encoder dot fit transform, that same column. So that's simply just going to turn f's to zeros and m's to ones. And to confirm that, we can create a new dictionary. Let's call it gender mappings, matching some index to a value for every index value pair in the enumerated version of label encoder dot classes. And this is an attribute that comes with the label encoder object that will basically give us, this is a list of the unique values in here in the order that it encoded them. So it's very similar to what we did here, where is it? Where's this one? Very similar to color ordering. You can see if I run this now, it's 0, 1, 2, but before it was different. Okay, so oh yeah, and let's just look at gender mappings. So you can see 0 has been, f has been mapped to 0, m has been mapped to 1, which is the standard convention. And let's take one last look at our data. You can see that everything is in numerical form, and not only that, but everything is in very similar ranges. The only thing that isn't either a 0 or a 1 is this favorite color. So we will actually scale it using a min-max scaler, just to be extra careful. So over here, from sklearn.preprocessing, import min-max scaler. Even though the highest value it can have is 2, it's just nice to have we'll have a 0.5 for 1 and a 1 for 2 instead. So we will split it first. Let's make this splitting and scaling the data. So our y is going to be the gender column, and our x is going to be everything except the gender column. Now we're going to scale the x with a min-max scaler. So we make a new object, and then x is going to be scalar dot transform x. And this will return a NumPy array, so let's go ahead and turn it back into a data frame and retain the same columns as we had before. Take a look at x now. You can see everything is floats, that's fine. This one, however, 2's have become 1's and 1's have become 0.5's. So now, let's split it once more into train and test sets. And this is using the train test split function that we imported from sklearn. And here we have just so few examples. I don't really know what to make the train size. I guess 0.7, because even though we have less to train on, if we have 0.8, our test set is just going to be so small, we're not going to have any idea if our model is actually doing well. Let's see, what's 30% of 66? It's 19.8. So we have 19 examples to test on, and that's if we have a 70% train size. So let's now train, and we're going to use TensorFlow. Actually, before we train, before we do this, before we even split it, why don't we just get a visualization of the correlations between our data. So plot.figure, I'll make another markdown, call it visualization, and fig size, let's make it 12 by 10. And we're going to use the seaborn function heatmap to generate a heat map of the correlation matrix, data.core. And we'll turn on annotations, and we'll just specify the min and max values and show that. Alright, and we can see hardly any correlations, right? The strongest correlations we can see here are between Coca-Cola and Pepsi and Fanta. They're negatively correlated. So the more someone drinks Fanta, the less they drink Coca-Cola. And nothing else, really. There's hardly anything in here. Gender is the one we're most concerned with. And the strongest correlation in gender is with pop music. Since the positive example is male, it seems that males tend to like pop less, but really it's not very strong. We don't have any strong correlations here. It's strange. The strongest correlations are between Fanta and Coke. So yeah, I mean, I don't have high hopes for this model. I don't. Let's start it though. We'll create our input layer, tf.keras.input, and the shape is going to be the size of our number of columns, which in this case is 18. Our first hidden layer will be a dense layer, tf.keras.layers.dense. Let's give it 64 nodes and an activation of ReLU. Pass in the inputs. We'll do the same thing. Whoops. Okay. Except here we'll pass in X. So we have two hidden layers, each with 64 activations. And then we have outputs, which will just be another dense layer, but only one activation, because this will just be the probability estimate for the positive example, and not softmax. Actually, we'll use sigmoid, and pass in X. Then our model is going to be tf.keras.model. We'll specify the inputs as we did, and our outputs as our output layer. Okay. Now we'll compile the model, And optimizer, we'll just use atom. Our loss, we'll use binary cross entropy. And our metrics, well, let's take a look actually before we say the metrics. If we take, remember y is just this array of zeros and ones. If we take the sum across all examples, that will give us the total number of ones, 33, and we know we have 66. So if we divide by the length of y, which is the total 66 number of examples, we'll get 0.5 exactly. So this data set is split perfectly between male and female, and that means we can just use accuracy. No need for fancy metrics here. Accuracy will serve just fine because we have no skew in the classes. And now we'll declare a batch size, just say the standard 32, and then number of epochs. We'll start training for 100, but it's such a simple data set, I don't know, it might overfit very quickly. Let's store our model's fit history in the history object, and we'll train the model on xtrain and ytrain. We'll give it another validation split of 20%, which gives us so few examples to learn from. And alright. Batch size will stay as we specified. And the same for epochs. And let's just turn off verbosity so that we don't clutter the notebook. Alright, that's training. Should be done very quickly. We'll start visualizing the results. So it's like what I usually do. We will set up a new figure with size 14 by 10, and then we'll set up the x-axis. We'll have epochs range. Will just be a range from 1 to the number of epochs plus 1, which this will give us a range from 1 to the number of epochs, since range starts at 0. Then train loss is going to be the history.history index.loss. So this object here has an attribute called history, which has all of our metrics and all of our losses for each epoch. And so if we index at loss, we'll get the training loss across epochs. And for val loss, we'll have the same thing, but indexed at val loss. Now we'll plot on the x-axis the epochs range, and on the y-axis training loss. So I'll just label that. And then on the we'll do another plot, this time on the validation loss. We'll just title this training and validation loss, plot.x label, epoch, plot.y label, loss, and we'll turn on the legend. Show the plot, and wow, just as I suspected. I'd like to see this. Alright, there's 100 epochs here, but it doesn't look like our validation loss is ever even going down. Well, let's see. And numpy.argmin val loss will give us the epoch with the lowest validation loss. And it says 24. Okay, so let's try retraining for 24 epochs. Okay, that's just already done. Let's plot it again. And okay, so it looks like it's going down a little. Let's take the argument of this, 22. Okay, so it looks like maybe we're around the right place. So let's evaluate the model on the test set, and we get an accuracy of 70%. pretty decent. Let's try training it again, evaluating again, and accuracy of 60%. Let's try training it again, and I'm resetting the whole model each time I train this, so it's not like picking up from where I left off. I'm just trying to get a sense of if this is actually accurate, and it looks like we're actually it's hovering around the same area. 50%, okay, so maybe not. Although, yeah, you know, this doesn't seem too bad, but let's look at the length of our test set. There's only 20 examples. So it's doing better than a random guess. Essentially, this is a random guess, right? It's doing a little better, but not much. You know, this is more or less what I expected. In my earlier notebook, when I was working with this, I didn't ordinal encode this favorite color column. I just one-hot encoded it. And I wonder if it has something to do with the improvement in accuracy. Because when I was doing it, I was just getting terrible accuracies, 20%. And it doesn't look like doing too badly, 55. You know, there is some element of stochasticity in this. But it looks like it's hovering around the same range of about 50 to 70%. But I guess that sums it up for today. Bit of a weird one. You know, maybe there's some predictive power in these columns, these original columns. But if there is, it's not much, right? It's very difficult to classify gender, and doing it with such a limited set of data is a very strange thing to be doing. But thank you so much for watching today's episode. If you enjoyed it, make sure to subscribe and hit the bell, and leave any comments in the section below with any suggestions you might have for the channel. Thank you so much. I'll see you guys tomorrow. Have a great day.